Hello Year 11, this is your lesson on Pascal's triangle. Okay, have a look at this design and think about how I'm making it. If you haven't spotted it yet, pause the video and have a stare at these numbers for a bit longer and see if you can work out what the pattern is. Okay, so hopefully you notice that you can work out each number by adding the two numbers above it. We have ones going down the edges here. So the top row we call the 0th row, and so we're going to have a look at the 4th row now. Now perhaps you have noticed this. So 1 is 4 choose 0, 4 is 4 choose 1, 6 is 4 choose 2, 4 is 4 choose 3, and 1 is 4 choose 4. And this is the case for all rows of the triangle. So the second number in the row tells us what our n is, and then the position in the row tells us our r, where we start at position 0. Now, it's Pascal's rule that n choose r is equal to n minus 1 choose r minus 1 plus n minus 1 choose r for all r's that are greater than or equal to 1 and less than n. So let's have a look at that. For example, let's say we've got 4 and 2 from before. So 4 choose 2 equals 4 minus 1, that's 3, choose 2 minus 1. 4 minus 1, choose 2. So we can use this to work out extra information from information that we're given. Here's our rule. So if we say that n is 18 and r is 3, then 17 choose 2 plus 17 choose 3 is 18 choose 3. Okay, so the n equals 6 row of Pascal's triangle, and we're going to use that to find the value of 6 choose 3. So we only got to here on our slide earlier, so we need to generate the 6th row. So we're going to have 1, then 1 plus 5 is 6, 5 plus 10 is 15, and so on. So this 1 is 6 choose 0, 6 is 6 choose 1, 15 is 6 choose 2, and so 20 is 6 choose 3. Okay, pause the video now while you have a go at questions 1, 2, and 3. So, the sandwich shop, Subway, we're going to imagine there's 5 salad items. I don't actually know how many there are. I imagine there's more than 5. Well, let's pretend there's 5. And you can choose any that you want. We want to work out how many different selections there are. So if you were feeling particularly unhealthy, you would be able to choose no salad. If you were feeling particularly healthy, you could choose all the salads. So we could select no items. We could select 1 out of 5, and there's 5 choose 1 ways of doing that, 2 out of 5, 5 choose 2, and so on. So that gives us the sum of 5 choose all the numbers from 0 to 5. If we put that into our calculator, we get 32. So it's the sum of the 5th row of Pascal's triangle, or the n equals 5 row, sorry. Now, we could think about it in a different way. For each item, you have 2 choices, accept it or reject it. Say, yes, I do want the jalapenos. No, I don't want the jalapenos. So, using the multiplication principle, we can say that there's 2 times 2 times 2 times 2 times 2, or 2 to the power of 5 ways of choosing salad. That's 32. obviously they're the same. And so what we can summarize from this is that the sum of the entries in row n of Pascal's triangle is equal to 2 to the power of n. This is a useful and a powerful result. And another way we can describe this is a set of size n has 2 to the power of n subsets, which include the empty set and the set itself, where n choose n is the set itself, n choose 0 is the empty set. So we can use that to answer the question, how many subsets of the integers from 1 to 10 have at least 2 elements? In total, there are 2 to the power of 10 subsets of a set of size 10. There are 10 choose 1 subsets containing 1 element and 10 choose 0 subsets containing 0 elements. So we're going to use the method that we had a look at last lesson with the, rather than saying how many are there that have 2, say how many are there that don't have 2 and subtract that from the total amount. So 2 to the power of 10, subtract 10 choose 1, subtract 10 choose 0. So that's 1024, subtract 10, subtract 1, which is 10 to, no, I don't know why I can't say that, 1013. Okay, so you are now able to answer the remaining questions from this exercise. Let your teacher know if you have any questions. Okay, so there's a few interesting things that we can find in Pascal's triangle. This isn't part of your course, this is just purely interesting stuff. So far we've already got that the total of each row is 2 to the power of n for the nth row. What you probably have noticed already is that this, the second diagonal in, is our counting numbers, our natural numbers. What you may not yet have noticed are these numbers here. Have a look at them and see if you can work out what group of numbers this is. Okay, so these are our triangle numbers. Triangle numbers are the number of dots required to make up an equilateral triangle of growing sizes. This row here, diagonal, make up the tetrahedron numbers. So if I were building a tetrahedral tower, this is the number of balls I would need to make ever increasing ones. So you see we've got 1 here, and then I would add 3 to get to the second tetrahedron. I would add 6 to get to the next tetrahedron, and so on. Now, the ever-increasing sizes of square-based pyramids, made of spheres, they're not quite so obvious. But I've got 1, and then I've got 4, so I can add 1 and 4 together to get 5. Now for the next one, I've got to add 9 to get 14. That doesn't give me 14 if I add the 10, but if I get rid of the 1, then that adds up to 14. Then to get the next 16 is the grey spheres on the bottom there. That makes 20, so that's the next pair along. So the square-based pyramid numbers are generated by adding consecutive pairs of numbers from this diagonal here. Now, Pascal was a very interesting mathematician. He also took a foray into philosophy every now and again. If you're interested in reading a bit more about him, you can pause the video and have a look through this. Another interesting result appears if we consider shallow diagonals. So what do I mean by a shallow diagonal? So if I take this as my first one, then these 2 red ones. So can you see the angle is less steep each time. Less steep than the diagonals I was doing before, which were like this. Now, if I take the sum of the numbers in the shallow diagonals, hopefully you recognize this sequence that appears. This is called the Fibonacci sequence, named after Leonardo Fibonacci, or Leonardo of Pisa. And you may or may not know the history of this sequence. It started, so Leonardo of Pisa set it as a maths problem about rabbits procreating. And yes, I think we mentioned the Fibonacci sequence in the golden ratio lesson as well. So it's nice to see how these things all tie together. So there are a few interesting things that you can find in Pascal's triangle. There's loads more if you are interested in searching for them. Thank you very much.